So I'm very excited to share this paper, which is titled An Outcome Test of Discrimination for Ranked Lists. And this is joint work with my great co-authors, Guillaume and Yinyin. So to set up this paper, there's a large literature in many disciplines, including economics and computer science, focused on detecting whether a decision maker, either a human or an algorithm, is biased against particular groups, say women or minorities. And the canonical setting studied in this literature involves evaluating a binary decision on the part of the decision maker, say, should we grant a defendant pretrial release? Should we give a potential borrower a loan, or should we admit a student to college? But in many practical settings of interest, the decision maker produces not a binary decision, but a ranked list of candidates. So this is going to be particularly relevant for online platforms where, say, Google produces, a search list of websites. LinkedIn produces search results of candidates meeting various criteria. And a variety of social media platforms produce ordered lists of posts in a feed. And in addition to being relevant online, ranked lists are also relevant in certain settings with human decision makers. So for example, hospitals rank potential residents for the National Residency Match Program, or in a variety of lab experiments in psychology and experimental economics. People ask participants for preferences over, say, which of the other participants would they be interested in working with. And so in this paper, we're going to think about how can we test for bias in the context of settings where the decision maker, be it a human or an algorithm, is going to produce a ranked list. So to give you an overview of what we do in this paper, we develop tests of bias in ranked lists in the spirit of the definition of bias first proposed by Gary Becker in the 1950s and used throughout the economics literature on discrimination. So in particular, we're going to ask, does the ranker sort candidates based on the expected value of their outcome? And what we'll show is that a sharp testable implication of unbiased behavior, according to this definition of unbiasedness, is a set of moment inequality restrictions. And intuitively, these moment inequality restrictions say you shouldn't be able to flip the position of adjacent candidates whenever you see a particular orientation of groups in the list, say men first and women second, and by doing this flip, systematically improve the objective on average. And we'll then illustrate how these inequalities can be tested statistically, and we'll show that the tests seem to work well in a validation exercise using data from LinkedIn. So let me just dive right into the model that we use in this paper. So in the model, there's going to be a ranker and an auditor. So there are going to be queries indexed by Q, and for each query, the ranker is going to observe J candidates with characteristics given by X and group status given by G. And then the ranker is going to produce a ranking of the candidates, which will denote by J of Q. So J of Q1 is the index of the candidate who's ranked first in query Q. J of Q2 is going to be the index of the candidate who's ranked second, and so on. And so in our setting, the auditor is going to observe the ranked list of candidates in order. So they'll see the outcome YJQ1, the outcome for the person ranked first in the list, the outcome for the person ranked second in the list, and so on, all the way to YJQ of capital J, the outcome for the person ranked last in the list. And then likewise, the auditor is going to observe the group statuses for each person in each rank. And then an important thing here is we're going to assume that the auditor does not observe the characteristics X that are used to form the rankings. In the paper, we extend this easily to the case where X is partially observed. So Why do we do that? Well, we think this captures a realistic restriction in many settings, including the work we did at LinkedIn, where the auditor may not observe all the information that is used by either the human or the algorithm to determine the ranks. So for example, at LinkedIn, even though we were internal to LinkedIn, because of data privacy rules, we actually often don't have all of the features that are used by the algorithm to construct the ranks. And certainly that will often be the case if you're an external auditor, where you won't be able to see into the black box of what features determine the rank. All right, so let me now tell you about the definition of unbiasedness that we use in this paper, which we think of as a natural extension of the notion of unbiasedness proposed by Becker for the case of binary decisions. So intuitively, we'll say that the ranker is unbiased if they sort the candidates by the expectation of some outcome Y, given their covariates, sort of regardless of the group status of the people in the list. So to formalize this, we're going to test that the ranker sorts the candidates to maximize the expectation of some objective, where the objective sort of sums the outcomes for people at different positions in the list, but places more weight, WR, on candidates that are ranked earlier in the list. So for example, if the decision maker wants to maximize clicks, regardless of the group status of the people in the list, and if we think of YIQ as the clicks a person get if their post is seen, but people earlier in the list are more likely to be seen with probability WR, then we would get exactly this objective where we rank the outcomes for people earlier in the list higher in accordance with these probabilities of being clicked if you're earlier in the list. And in addition to maximizing clicks, you can also cast other objectives that people often use in rankings context. For example, net discounted cumulative gain, which is a common objective for ranking algorithms, can also be put into this. Just a few thoughts on this definition of bias. So as I mentioned, intuitively, this definition of unbiasedness is asking, does the ranker sort candidates by their expected value of Y, given the observable information for those candidates? So in economics, this is typically called accurate statistical discrimination. In computer science, we would call this sorting the candidates by a Bayes optimal score. And so an important caveat about this definition of unbiasedness is that it depends on the outcome that you're using to test for unbiasedness. And in particular, for this type of definition of bias, we may detect bias if we use a particular outcome Y, but instead the ranker is maximizing a different objective, say Y star. That is, we have biased labels or omitted payoff bias. So as a particular example informed by our work at LinkedIn, if Y is whether a recruiter clicks on a candidate and Y star is, say, the candidate's true qualification, removing recruiter bias, then an algorithm that sorts candidates based on the expectation of their true qualification, Y star, may be determined to be biased if instead of using Y star, we use the recruiter behavior Y as the outcome of the test. All right, so the main theoretical results in the paper are as follows. We show that a sharp testable implication of unbiasedness in the sense that I just described is the following set of moment inequalities, which says intuitively that if we have a candidate who's ranked higher in the list, they should have a better outcome than a candidate ranked lower down in the list, regardless of the group status of the candidates in the list. So in other words, we shouldn't be able to improve the objective on average by swapping candidates in position R and R+1 whenever we see a particular group orientation. So for example, we shouldn't be able to improve the objective if we flip candidates 1 and 2 whenever candidate 1 is male and candidate 2 is female. And in the paper, we walk through how one can conduct statistical tests for this system of moment inequalities using statistical results from the moment inequality literature in econometrics. And in the paper, we think about several important implementation details, such as adjusting for the fact that the outcome Y may actually be affected by position, dealing with sort of a variety of other statistical problems. So to wrap up, let me show you how we kind of validate this approach using an exercise with LinkedIn data. So we focus on what's called the Insta jobs algorithm at LinkedIn. So for background, this is an algorithm that sends notifications about job postings that a user may be interested in if a relevant score is above a particular cutoff. And so an important note here is that this is not a ranking algorithm per se. As long as you get a notification, it doesn't matter what your score was. But to validate our approach, we can create a ranked list by sorting the candidates based on the score that the Insta jobs algorithm uses for each jobs. And so this is going to be nice in the sense that it's going to allow us to validate the proposed test by comparing the results that we get for the lists that are produced by this algorithm to what we would get if we examined the score directly, which is not something that we can typically do with a ranking algorithm. So to show you the results, here I have some graphs where on the left, what I'm doing is I'm comparing queries where we have a where we have a woman ranked higher in the list and a man just below them. So for example, the point here corresponding with 1 on the graph compares queries where there's a woman ranked first and a man ranked second. And what you can see here is that these differences are all negative, and for many of the ranks statistically significant, meaning that the man ranked just behind the woman actually has a higher outcome. And so this is evidence of bias in the sense of Becker, in the sense that it rejects the hypothesis that this algorithm is sorting candidates based on their expected outcome. If we look to the right panel, we're instead comparing higher ranked men to lower ranked women, and we can see that indeed the higher ranked men do tend to have higher outcomes. And the results of this test using the list rise rankings algorithm do indeed correspond with what we would get if we looked at the scores directly, where we see here that this score is not well calibrated by gender. So for men and women with the same type of score, the male candidate typically has a higher outcome than the female candidate. And so an important note here is that in part based on this work, this version of the algorithm has subsequently been deprecated at LinkedIn. So to kind of wrap up, in this paper, what we do is we propose a test of discrimination for ranked lists, extending the framework of Becker for binary decisions for the case where we test whether a decision maker is an expected utility maximizer for a ranked list. And our approach using this notion of discrimination is complementary to a variety of other approaches for ranked lists based on different criteria, such as demographic parity, disparate treatment or impact, or equal opportunity. And as is the case with binary decisions, there are kind of many different trade-offs between different notions of fairness, which generally tend to be incompatible with each other. And so I refer people who are interested to some of these great papers by Corbett Davies and Gall and Rambachan et al., where they discuss the pros and cons of these various notions of fairness. And so then to conclude, let me just mention that in ongoing work, we're kind of working on applying these tests to other ranking algorithms at LinkedIn. And then we're also working on ways to think about whether these results are affected by the fact that the labels may be affected by recruiter biases. So for example, in the application that I just showed you, we see that men and women at the same, who are ranked adjacently, the men tend to have better outcomes, but could that be the result of the fact that these recruiters are actually biased against women? So it may be that the algorithm is consistent with sort of an objective ranking of the candidates based on their true criteria that once you sort of remove the biases from recruiters. So thank you very much.